Yeah, thanks. So, for the invitation, the organizers for giving me this great opportunity, and thank you very much everyone for joining this session. Why? So, I'm talking about spacecraft. And this talk is based on a joint work with Bauer, who is coming to this workshop next week, and I'm here then. The overview. On the space of spacecrafts, there's only one symplectic structure known. This time, we find more. I want to explain how we do it. I want to also share with you the resulting Hamiltonian dynamics out of these new symplectic structures on the space of spacecrafts. And probably you guys already know what a symplectic structure is. I'll share here my understanding of symplectic structure. A symplectic structure is kind of a sandbox for Hamiltonian dynamics. In a way that you can just give a function value from Hamiltonian H, and then this symplectic structure omega produces dynamics. The way it works is symplectic structure omega is a true form that is closed and non-degenerate. And yesterday we added one more condition, but I'm not going to dive into this. And then you get a Hamiltonian vector field, pH. Satisfied with this relation. And Hamiltonian dynamics is this vector field. Right. And there are many physical systems that are modeled as Hamiltonian systems on different symplectic spaces. Like the theorem mechanics, the Schrödinger equation, incompressible fluid motions, and so on. And in this book, I want to focus on the space of spacecrafts. Or I want to first introduce parametrized spacecrafts before going to the shape space of unparametrized spacecrafts. When I say parametrized curve, or like parametrized curves, this is just a collection of immersions from S1 to R3. That are just maps. There are nowhere easy. And tangent space at each point, which is a curve, is again a map from S1 to R3. You can think of like any tangent vector as a vector field, like these green lines, over your curve. The sum expressed as the infinitesimal perturbation or the velocity of your spacecraft. And I can take away parameterization by modeling out the orientation preserving diffeomorphism of S1. And I now lost parameterization but have orientation. In a way, you can think that the space of immersions as a principal diff plus S1 bundle over the space or the shape space of unparameterized immersions. Yeah. And the tangent space is just a tangent space and the immersions modular kernel of the vibration pi. The kernel of the pi looks like this. And this is just a collection of tangent vectors or vector fields over the curve that do not change the shape of the curve. So this is a vector field tangent to the curve tangent. And you can identify this with the tangent vectors, with vector fields over the curve, perpendicular to the curve tangent everywhere. And this is a tangent vector space. The space of unparameterized immersions. By the way, some people say like unparameterized immersion is kind of contradictory because immersions have parameters, but this notation. And it's known that this space of unparameterized immersions has a symplectic structure called the Marsden-Weinstein form. Symmetric form that looks like this. So in order to emphasize the equivalence class, I did use like this bracket or sheet and okay. This looks like this. And ds means the derivative with respect to the occurrence parameter. And this like small ds guy is again integral element with respect to the occurrence parameter. And curve x is just a cross product in R3, and like this bracket is usual inner product in R3. ESI is just a unit tangent, and at each point of the curve, I can measure the volume of this shear cube spanned by my unit tangent, DSC, and H and K. And I can integrate this quantity over my curve to get some real value. And this is the Marsden-Weinstein form. And this is symplectic. And remember, we need two things. First, closeness. First, you can check it. And also, it's non-degenerate. So the kernel consists of the equivalent class of zero vectors. It comprises all the tangent vectors or all the vector pairs of the curve that do not change the shape. This is symplectic. And let me show you an example of Hamiltonian flows. This guy is called the binomial flow. Some people call it Bauer experiment. So like I feel the length function of the Hamiltonian. And as a result, I get this like binomial times curvature vector field. And it looks like this. So my curve is evolving under this binomial flow. And this is not to be a completely integrable system. This is one example of a Hamiltonian system that you can get from the Marsden-Weinstein structure. Now let's remember, like, the symplectic structure omega defines the Hamiltonian vector. Of course, if you get another symplectic structure, this should give you another Hamiltonian flow. So far, only one symplectic structure omega is known on this shape space of unparametrized imagines. But we found more. And we did it by combining two hints from different fields. The first hint is from so-called shape analysis. Like this guy. He defined the Riemannian metric on the space of imagines. I just take the inner product between H and K, and I integrate all the samples. And this is this L2 inner product is a starting point. And like there is a trend to plug some nice operator in from the tangent bundle to its set to get another metric. Like I did not buy GL. The new method that I get just by plugging in to H of K. And usually I assume L is self-adjoint. So like applying H or K doesn't mean matter. Yeah. Anyway, maybe I can get a new metric if L is a nice enough operator. And this is the first hint from shape analysis. And the second hint, I'm not sorry. We are going to the second hint. I'll give you some examples. So if I pick up L, just being an identity operator, nothing changes. I just got L2 in a metric again. And if I pick up a function of the curve that we call a conformance factor, I can sort of magnify my Riemannian metric everywhere with a weight coming from the curve sheet. Like this indeed defines conformal Riemann metric on imagines. This is another example. And you can also plug a local operator, like Sobolev type differential operator, identity minus second twice with respect to the arc length parameter. Then by performing the integral by parts, you can develop like this define indeed a Sobolev type Riemannian metric for the space of space cars. Right. So this is the first hint. The second hint is actually the Marsden-Weinstein form is not only closed but also is exact. Like there is some one from theta. So they say derivative gives us the Marsden-Weinstein form omega. And this theta is often called the Liouville form. And theta looks like this. Like how this guy looks like isn't really important. What is important is like theta can be written in terms of something and the vector h. Right? Naturally, maybe you can combine hint f1 and hint 2. For example, I can define another one form just by plugging that to h. Then theta. This depends on another one form. Obviously, I can take the exterior derivative of this guy to define another two form. The question is this really a symplectic structure of shape space? So remember, we needed two things: closedness and non-degeneracy. And the closedness is automatic because it's exact. What about non-degeneracy? Like we needed this, the current is trivial. It turns out that this has to be checked case by case, and it turns out that it's surprisingly difficult to check this non-degeneracy property for very generic operator. But anyway, we managed to show this non-degeneracy property for a simple case. That's this theorem. Like for conformal factor lambda on the shape space, then we can obviously get this like two form omega lambda. In the process that I explained, this guy becomes a symplectic structure on the shape space under some strange condition. If the one form theta lambda is not invariant under the scaling of the curve, then this indeed defines a symplectic structure in the shape space, and this is non-degenerate. So what if theta lambda is invariant under scaling? If theta lambda is invariant under the scaling of the curve, omega lambda, unfortunately, does not define a symplectic structure on the shape space, but this can become symplectic in another space, which I find very interesting, but I don't explain it because I don't have much time. So if you're interested as well, please check out our link. So, as I said, different symplectic structures, of course, define different Hamiltonian laws from the same input Hamiltonian. So I'm not sure how Hamiltonian vector field looks like. This is our Hamiltonian vector field obtained from this like conformal factor symplectic structure, and this looks quite complicated. What is it? Or instead of explaining these terms contained in this, I will just show you some visual example. Okay. So for this, I pick up a specific Hamiltonian function, the total square scale. Like I just take the square scale and integrate this over the circle. And I give three different symplectic structures. The next one is a classical Marsden-Weinstein one. And I have like in the middle and in the right, I have two different symplectic structures coming from different choices of conformal factors. And you can see that like, the Hamiltonian dynamics are very, very different, at least visually. In particular, this rightmost one is like this guy looks almost static, but like this is nicely forming kind of complex spirally pattern as time passes. And remarkably, of course, the Hamiltonian edge is preserved in all of them, but the dynamics are very, very different. And so this is what we got for space curves. And the actual question is, can we do the same job, same machinery to other spaces to get kind of more symplectic structures on other spaces. And I did some experiments recently, and I got some results. So let me show this. This guy, because we are usually an institute. So let me talk about something related to this guy initially. There are other these contributions that this equation. So, okay, like I dropped the potential term, so like this guy is now called the linear Schrödinger equation. It's known that this is a Hamiltonian for this Hamiltonian for the nuclear energy on the function space, the complex function. Here I chose like some like d-dimensional torus, but this doesn't really have to be a torus. This can be any Riemannian manifold. For simplicity, I just torus. Anyway, with a certain symplectic structure, the linear Schrödinger equation is a Hamiltonian form. I don't like this symplectic structure omega. What is important is, again, omega is exact. So we can get a liquid form of omega. Yeah. The natural question is the same using different operator there from the tangent bond to itself. And get more symplectic structures. And the answer is yes. And it has a own sequence. Well, I got some proposition. Like I have a family of equations that looks like this. Like this left-hand side, the first term is same as the Schrödinger equation. I have like I and the time derivative of psi, plus some big operator, which is 1 minus a1 Laplacian minus a2 by Laplacian. And it goes on, and minus an and Laplacian to the nth power. And finally, I take the inverse of this big operator and apply this to Laplacian psi. And like these coefficients can be anything, as far as they are non-negative. So the area of the Hamiltonian system was the same Hamiltonian equation, but with respect to different symplectic structures on this function space. And actually, all these equations are explicitly solvable. I can visualize them. So this is the standard Schrödinger equation. And at the initial condition, I get some like a Gaussian like wave function, and I add some velocity by adding some wave number. And I'm visualizing its intensity. I'm like squared psi. This is a standard Schrödinger equation. And then the next one. I got some like non-zero A1. Like 1 minus A1 Laplacian and then that case. And maybe some of you guys already expected, like this is somewhat smooth or blurred. It's kind of expected. And the next example is, okay, I got some like non-zero A2. 1 minus A2 by Laplacian. And I take the inverse of like this entire operator. And at least to me, it is very surprising because like it seems like the direction of the wave is somewhat reversed. Like these two, in these two guys, like the waves are moving this direction, and this is somewhat reversed.
This is for all values of the parameter A2.
Excuse me.
The parameter A2.
Yeah.
You can choose it.
Yes.
As long as it's not 0, I guess, because otherwise you are in there.
As long as it's not negative, yes, you can choose whatever A2. Like A2 can be 0 as well, but if A2 is 0, this is just a linear Schrödinger equation.
But the square of the Laplacian is a positive operator. So the square of the Laplacian is a positive operator. So if you put a positive coefficient and a minus, that could be 0 at some point, for example, A2.
No. Minus.
Okay, it's minus.
Yes, minus A1, minus A2, minus blah. Okay. Yeah.
But what will happen if we simply do Fourier transform in this situation?
Yeah,
But
maybe
you
there's-
Fourier transform and get a collection of ordinary differential equations.
Yeah. Yes.
But
This is
certain
this is
sense
how I
source.
can make all explicitly solvable. You know, like we can translate all the terms, and we can, you know, like solve this in the Fourier domain, and we can come back from the Fourier domain to the real domain. And yeah, we get solutions. Wow.
The solution depends on we decompose your polynomial in product, and it will be something with many confluent hypergeometric functions.
I don't understand.
Solution, it seems to me that solution will be in terms of confluent hypergeometric functions.
You mean by factorizing the polynomial?
This is polynomial, we factorize it, after this we get something with fractions. But maybe I'm not right, since it requires calculations. I'm not mathematician, according to the definition which was given today. I can write formulas.
Yeah. Probably I think we should talk about this later, you know, so that I can fully understand your question and your point, and yeah, we can discuss it. Yeah. Well, thanks for coming. Yeah. And I learned that like this semi-real behavior is coming from something called like semi-relativistic approximation of the quantum Schrödinger equation. I'm not going to dive into detail, but like it's related to relativity. Yeah. And then concluding slash future work. Like I hope to make some kind of paradigm that people differs not only the Hamiltonian, also the geometric or symplectic structure of the state space. And for modeling many kind of natural phenomena, like relativistic Schrödinger equation. For example, like people tend to tweak the Hamiltonian of the Schrödinger equation to make it somewhat relativistic in a way that the speed of your particle never goes beyond the speed of light. So I personally find that a little bit artificial. I think like if you want to get like a relativistic phenomena, probably like you should change the physical law of the law. Meaning that like, you should probably change the symplectic or the geometric structure of your world so that you have a new physical law. That maybe like prevent the particle from going faster than light. Yeah. In this way, like I have more like this. For example, relativistic Schrödinger equation and yeah. That's it. And the preferences are available on the archive. And by the way, I'm on the job market in 2025 autumn and later. Thank you very much.